Hello everybody, and welcome to today's Midas Gen webinar. Today's session will cover a building extension done in central London by one of our clients, Structured Environment. These are the topics of today's session. We will look at an overview, some of the challenges that such a project imply, some of the requirements of the Eurocode, then the structure itself, and afterwards we'll look into how all of this was done in Midas and how the software can help us with modeling such a structure, and also the design feature and some results. There are many old buildings in the UK, and in London especially, many of these have an historical past. This makes for the demolition of such buildings almost impossible, so the laws for this are very strict. That's why it is very common nowadays to have either building extensions or remodeling of such buildings without changing the exterior too much. It is one of the most common trends is that of having loft conversions. This is one of the cheaper alternatives, and there are many such projects in London especially, and some of them are even covered in shows such as Kevin MacLeod's Grand Designs. Another alternative it's converting the basement. This is a more expensive alternative, as some of the requirements for the structure inside are much stricter than for loft conversions, but in any case this is a good alternative as well. You can see on the right hand side a picture of such a project as it was ongoing, and on the left you can see the finished project. How can this look very good? How this can be a very good alternative. Today's project covers an extension of an existing building. The building is a 5-story masonry building with solid floors. This is located in central London, and originally the building was built in the 1600s, and it was used as a warehouse or a factory. The project, you can see other views of the existing building. On the right you can see how the building looks from street level, and also the structural elements after they were put on the building. And on the left you can see a view from the roof level. Again, we can see the structural elements, and this is a proposed render. The idea of building something like this on the existing building was after a person acquired the rights to use the roof level of this building to build something on it, and it was after discussions with the client and with the local authorities. A 2-story extension was decided. Many conditions come from local authorities, such as the looks of such a building, of such an extension, and how this affects the environment. Also, a poll has been created for the neighbors, asking about the future building, and their opinion and requirements have been taken into account as well. And also, obviously, the requirements from the client. The new extension had to have as much area to be lived in as possible, and at the same time staying within the requirements of the local authorities. Now, the Eurocode, the building has been designed, the new extension has been designed according to Eurocode, and Eurocode, as you know, has some requirements for the loads. The dead loads for this building came from the structure itself, the dead loads, and also the load coming from the timber floors. These were in specs of 0.6 kilonewtons per square meter, but for this project a value of 1 kilonewton per square meter was used. Also, live loads needed to be taken into account, also vertical live loads as well as horizontal live loads such as wind, and these have again to be considered as per the Eurocode with the requirements for the height of the building. All checks have been done according to the ultimate limit state and the serviceability limit state. Now the structure itself, the floors were done using timber construction. Also the walls and roof were prefabricated panels to allow for an easier installation, and also to help with the lateral loading, braces were considered for the frame. The structure itself was done using steel frames, and these for the roof a steel grillage was used to support the loads so that the roof of the existing structure is not loaded too much. Also cross bracings were used as mentioned before to help with the lateral movement. There are many requirements for such a building, such as the way the loads are distributed to the structure. So, for example, local authorities imposed rules such as the fact that the walls of the existing building, of the new addition, of the newly constructed structure needs to be about 200 millimeters inside of the walls of the existing structure for the first floor, and for the second floor this had to be modified to about 500 millimeters. These implied a bit of a challenge because a suitable solution had to be found for the lower joint and also for the connection between the top floor and the bottom floor. Now, modeling in Midas was done using the modeling can be done either by drawing the structure directly, but as the newly added structure had to follow the existing structure, an AutoCAD plan has been used, imported into Midas Gen, and this was and the structure was afterwards created. I will now go into the software and show you how this can be done. I have here a model with material and all the sections that were used in the model used for the analysis, and we can simply import a DXF file here. Importing the levels, and here I have the first level of structural elements. This is at the ground floor. This is at the roof level of the existing structure. Then the beams for the second level and the roof beams. Now, as we have these are going to be the structural elements, so now we can just simply place these at the right positions, simply selecting these elements and translating them using move and deleting the existing elements. So we can simply choose a reference point, and as these are at the same level, we just have to change the level of the second row of frame elements. So we can simply add in like this and now we have the floor added, and we can do the same for the roof level. Adding the correct coordinates. And now we have all three levels created. To create the vertical elements, we can directly use an export function, an extrude function. So we can select the nodes here using select by polygon, and deselecting the nodes that are not of interest now. So now simply we can project all of these elements onto this line, assign the section of interest, and then simply apply. After having these elements, we can do the same for everything, and we can also create the braces. As mentioned before, we have bracing elements for this structure. We can either create truss elements directly, or we can use general beam elements and simply assign beam end releases. So from boundary we can add beam end releases, simply select the element and choose which degrees of freedom we want to release. So in this case we're releasing rotation about my and mz. After importing everything and adding in geometry, we can assign the correct sections to the elements. Now, when it comes to loading, the vertical loads representing the dead load and the live load were added using one of the functions in Midas Gen called floor loads. This is very helpful as we can create specific types of loads in which we can assign the values that we need for different load cases. So we can define a load over an area, and all the loads are transmitted according to the input that we choose, according to the distribution that we want. The loads will be distributed to all frame elements, and we can also copy this at different levels. Now here I have the completed structure. As you can see, all the frame elements and the loading as well. We can use the self-weight function for the self-weight of the structure elements, and for the rest of the vertical loads, as mentioned before, we will use the floor loads. In the load type, here we can create different floor loads. So for example, the timber floor load type was created, and we assign in different load cases the different values. And for the roof again, we can create the same, each with the appropriate values for the loads. And afterwards, to assign the loads, we simply choose the type of load that we want, the type of distribution, and then assign an area. So let's say something like this. I'm not going to click apply to not override the result, but after applying we can see the loads applied on all the frame elements with the correct distribution that we have chosen. Now for the lateral loading, it is very important to consider the correct loads, and Midas Gen has a very useful function called story data, which stores information about all the floors in the structure. For this we can choose the levels of each floor, so loads, vertical loads such as earthquake load or wind loads will be added corresponding to the height of the building. And also this function helps us choosing what type of behavior we want for the floors, if we want to consider a rigid diaphragm for the floor or not. If we were to consider rigid diaphragm, then wind loads would be applied at the geometric center of the building, but in this particular project it was intended to add the loads at the intersection of all frame elements, so that the lateral behavior of the frame can be simulated in a more correct way. So here we can see the wind load added as per the Eurocode. The wind load, again, as mentioned before, considers all the information as per the Eurocode. We can choose the terrain category, friction coefficients, direction of the wind, and everything is as per the Eurocode. We can also see the wind profile for each level, and the story data can be seen here. We have all the levels defined, and each level corresponding to the actual level in the real structure. So in this way the wind loads will be calculated, the wind profile will be calculated as per the code appropriately. And also, if we want or not to consider rigid diaphragm, also information about information that will be considered for wind and for seismic loads. This is again the explanation for the wind loads. As mentioned before, this was done as per the Eurocode, considering all the loading conditions and coefficients from the Eurocode. The load combinations in the model, as mentioned before, the design was done as per the Eurocode, considering the ULS and the SLS combinations. Midas Gen has a function in the still design to auto-generate load combinations, and all of these were auto-generated by the software. And also a very useful tool when considering load combinations is the envelope, which allows to create a load combination that includes all existing load combinations separated into strength and serviceability, which take the maximum and minimum, the critical effects in all elements, so that we make sure that the design is done to the most critical effect. In the software, the load combinations can be seen here. We can auto-generate them, as mentioned before, or we can create them manually, and also the envelope load cases. For this project, also a very useful tool was used, the design tool. Design tool allows to use the to check as per the Eurocode. So we say we have an element, we carry the still design check, and we can see the checks either in graphic format. We can see information about the units of system, which member we're analyzing, material properties, section properties. We can see the section properties also in a graphic format, the design loads used, and also the design parameters, the effective length, and also then the checks, actual force checks, bending resistance checks and the combined checks, as well as the shear, and also deflection checks. The software automatically takes the real load, the real deflections from the software, and does the checks as per the imposed conditions. For example, if we were to check the deformations under, say, an SLS load combination, we can see that if you were to check the vertical values, we can see the values in the visually, or we can check the values at each point, and these are global results, but the design tool automatically checks the actual deflection of the elements, considering the displacements at the ends as well. In cases where for example, more elements are joined, such as, let me isolate this, such as the level here. We have two cross beams connecting to one beam element. Normally this will be considered as a beam element, this as one and this as one, but this design tool allows us to define this entire beam as a member. So we can design the member, we can assign the elements for the member, and now the correct effective length will be considered for this. So if we do the steel check, we can see the values for the member with the correct length. Another useful tool in the design check is that of checking the ratios of the members. So we can check for each property, or for each member, or for the different materials, and we can check for different components, axial, shear, or combined, and we can see all of these in a graphic format. So now we can see the ratios here. For example, 0.64 means that 1, it is closer to the ideal usability of the section, of the strength of the section and the material, and as we go lower, this decreases. As you can see, in many cases for this project, many of the elements have a very low ratio. This is due to the fact that there were some height requirements imposed by local authorities, so the two stories couldn't be too high. So in order to have a usable space in the rooms, to have as much usable space as possible in the rooms, the sections have been kept to a smaller height, and in some cases, as you can see here, the section has been doubled. Instead of using a higher section, a section with a higher moment of a higher section, a deeper section, two sections have been used, two elements. Also, another useful tool in the design is that of the optimal design. For example, if we choose an element and check it with the optimal design, we can see the value of COM tells us the ratio of the elements, so how much of it is actually used. And if we want, we can select the element and run the design and the analysis for it, and the software will automatically give us the ideal section for this. For this particular project, this hasn't been used as there were strict requirements on the height of the sections. Also, when it comes to results, a very important thing to keep into account in this project were the forces that will be transmitted to the existing structure. So reading the reactions at the support conditions was very important. The support conditions for this has been considered as pinned, so all the columns are pinned at the roof level. The reactions from the load combinations can be read directly, and very important in this project was to keep the reaction values as close to each other as possible. As expected, the values in the exterior were smaller than the ones in the interior, and three types of systems have been used to transmitting the loads to the existing structure. One for those where the load coming from the newly constructed structure was about 152 kilonewtons, then one in the range of 100, and one for the ends. This was so that not too many different elements or two different elements to be used in the on-site, as to keep everything much smoother. The idea of this idea was used also for the frame, and some sections, even though they were over-designed or they were too big for this for their use, were kept as they are, so that to reduce the cost of fabrication and to make an easier job for the contractor. Now this is it for today's project, for today's webinar, and for this project. I hope you found it useful, and feel free to contact us on our email address, uksupport@midasgen.com, or to give us a call. And also for any news or information about upcoming sessions or events, webinars, please go on our website, and you can find all the information you need there. Thank you for your attention, and have a nice